All right, so I'm Philipp Moesta. I'm a postdoc at the California Institute of Technology. I'm working there with Christian Ort, and today I'm going to present you results that we've recently obtained with simulations on blue waters on how to explode or not explode massive stars with strong magnetic fields and rotation in full 3 dimensions. This is work that has been carried out with a large team at Caltech and also with our PI, Peter Diener, who's at Louisiana State University. This was recently published in the Astrophysical Journal Letters, and so you can go and have a look at this. So, core collapse basics, as Brian has mentioned earlier, and then the supernova goes off, and this is what we're trying to figure out. And this sounds very easy from like a cosmological simulations point of view, but if you're actually trying to figure out the detailed processes, this is actually a very complex and rich problem. So the basic story is that you have a massive star. At the end of its lifetime, it has exhausted all its fuel for the nuclear fusion, and then it kind of collapses on itself. The iron core collapses on itself. You form a protoneutron star. So as soon as you pack the neutrons so densely, you basically have this extra pressure that halts the collapse. This halt actually launches a shock wave that then runs out into the star. And this shock wave, however, is not able to explode the star initially, since it loses energy due to dissociation of heavy elements at the shock front. It stores at the typical radius of 100 to 150 kilometers, and then basically sits there, and we need to figure out a mechanism how to revive this star. So basically, we have this scenario with the stalled shock, and then we need to figure out how to explode this, actually. So the typical supernova actually believed to be exploded by the neutrino mechanism, where neutrinos that are emitted in the cooling of the protoneutron star deposit heat behind the shock front, creating extra pressure there and basically driving the shock wave outwards. However, there's a small fraction of supernovae which are very energetic. So they're typically a factor of 10 to 100 more energetic than the garden variety supernova that we observe. This is only 1% of all the supernovae, and these are type 1c supernova, and not all of them are also hyperenergetic. But a few of them have on top of that Doppler broadened absorption lines in their spectra, which indicates outflows of stellar material at high velocities that basically broaden these lines. And even though these are only very rare events, they're actually very interesting, since some of them are also connected now to long gamma ray bursts. So we're trying to figure out how kind of this connection between the supernova engine for these extreme explosions connects to the additional launch of a long gamma ray burst. So these explosions are typically deemed hypernova just because they're hyperenergetic. And so the basic evolutionary diagram here is that you basically have this core collapse, then you form some kind of engine for driving your explosion, and then there's basically 2 routes that you can go. One is the normal route to go to standard supernova. You explode the outer core and the stellar mantle away. You end up with a nice remnant. And then there's this extreme scenario, which is here on the lower part. Let me figure out. Yeah, this one here, where you basically have this hyperenergetic supernova and possibly a connected long gamma ray burst. So basically, we have 11 of these confirmed candidates now, where we have a long gamma ray burst together with a core collapse supernova. These are all these type 1c broad-lined supernova, which basically have no hydrogen, no helium in their spectrum. So that means basically that these stars have lost their envelope prior to explosion, either by winds or by binary interactions. And then as we go on, so the neutrino mechanism, I've already mentioned, this is not efficient enough to actually drive these kind of very energetic explosions, since it's actually a factor of 10 too low in energy. So which kind of mechanism can drive these explosions? And here we go to what actually has been proposed in detail already theoretically in the 70s, the magnetorotational mechanism, where strong and rapidly differential rotation interacts with strong magnetic fields in the progenitor star to actually extract energy that is stored in this rotation via the magnetic fields, and then deliver this kind of extra pressure behind the shock front along the poles of the rotation axis of the star. And then the outcome, which was believed to happen, was these nicely bipolar jet-driven explosions, where you have along the rotation axis these narrow jets exploding the star. So this has been studied in detail also with 2D simulations, and everything worked well. We got robust explosions. A few caveats that came in was that you need high core spin and you need strong magnetic fields on the order of 10 to the 15 Gauss after core collapse and after you formed your protoneutron star. So these are strong magnetic fields. And this would only apply to like a very rare fraction of progenitors, but it is possible. So this ties in nicely with the story of like having this only like in a few supernovas that we actually observe. So to go to the computational challenge, we wanted to see how does this work in 3D, or does it work in 3D? So to have a look at this, at what the core collapse problem actually poses, and it's basically a multi-scale, multi-dimensional, multi-physics problem. So we need general relativity to handle the protoneutron star and the gravity. We need magnetohydrodynamics to handle the explosion and all the fluid motion. We need the nuclear equation of state to have the proper modeling of how the neutron star stiffens in the center of the core. We need neutrino transport, which is, again, like another 7-dimensional parameter space. And we need neutrino and nuclear interactions. And then to give you a basic idea of the scales that are involved, so typical turbulence is on the scale of like at least 10 meters maybe for these problems, while the inner core actually that is relevant for just modeling the inner engine is 10 to the 9 centimeters. So this is like already factor 10 to the 6 in these different scales that we need to resolve. The other problem is like the time scale. So we need to do this in full GR. So we're current limited by the time step factor, and we have something like 10 to the minus 6 seconds for the maximum time step that we can take in our numerical scheme, while the cooling time of the protoneutron star is actually something like 10 seconds. So this already gives you a quick idea of like how complicated it is to actually model these things in full detail. And then, so basically we have 3 spatial, 3 momentum dimensions for the neutrinos, the time dimension, and all of this needs to be done in full 3D, since turbulence and also like instabilities that might come into the game actually are naturally 3D. So if you, for example, try to model turbulence in 2D, you might get a wrong saturation behavior of where your magnetic field grows to, or you might actually get the whole dynamics wrong. So what we've done is new 3D simulations, and those have been carried out in Blue Waters, and Blue Waters was essential in actually being able to carry out these simulations. This is based on our community toolkit, the Einstein toolkit, which is an open source collection of code components that can be used to like simulate general relativistic scenarios. So this can be done for binary neutron stars, for binary black holes. We use it for core collapse. This is all online at einsteintoolkit.org, so you can go and check it out if you like. This has been published in a code paper as well. So basically, this uses full GR. We have a detailed nuclear equation of state that is basically in a table, so that we go in and look up what is the value of the pressure for this given temperature, or what is the value of the internal energy. So this makes it complicated since we need to do a lot of interpolation. Then there's basically an approximative neutrino scheme that basically is not a full transport scheme, since for 3D simulations that would be too expensive at the moment. But we go in and basically approximate the energetics of the neutrino effects correctly to at least an order of magnitude, which for now is good enough for us, and especially in this scenario, which is not neutrino dominated. To give you an idea of the simulations, we use adaptive mesh refinement, which is crucial to actually place resolution where we need it and still being able to actually put the inner iron core on our grid. So we typically use 9 levels of this. This is basically just a factor of 2 difference in resolution from level to level, so it's not even fully adaptive in the sense that it's dynamically moving around. We have a nicely spherical symmetric problem to begin with, so we can actually just put our boxes in the interior and then basically make sure that we keep the shockwave that is running out on the grid with the resolution that we need. Still, we have like 6 terabytes of runtime memory typically for one of these simulations, and 500 terabytes of simulation output, which actually pose to be quite a difficult problem just to visualize it and handle those big data sets. And that's where also like I like to thank the Blue Waters team, since they've been kind of crucial in actually making this possible. So typically our jobs are kind of small, I guess, considered for Blue Waters, since we only run on like something up to like 20,000 cores of the machine. We use OpenMP and MPI in a hybrid fashion, since that proved to be most effective for our code. And the way that we're limited to 20,000 cores is mostly that we need to synchronize and communicate a lot of data between the different processors around, since we basically have so many different mesh refinement boundaries. And already Blue Waters enables us to actually push to 20,000 cores, which on other machines we actually can't so efficiently. So in that sense, that's a big plus with the communication network on Blue Waters. So let's have a look. How does this actually look like? So what I'm going to show you is a video of, on the left, a 2D simulation. On the right is 3D simulation. You see basically entropy, which is a good indicator for how hot material that's moving around is. You see basically this initial shockwave has already stalled. Now on the left, you'll see in a short time that there's basically these 2 jets pushing out along the polar directions, while on the right it looks like it's actually trying to do the same thing, but then something is going on and it actually fails and it falls back into like a nearly spherical configuration. So basically, these simulations are exactly the same besides for the 2D versus 3D. So all initial conditions, the code is the same. And so that basically on the left leads to a jet-driven explosion. This is a model that was actually done before in the literature, and we obtained pretty much exactly the same results that they had, only that in full 3D, it doesn't really work. So for a second, this freaked me out, since I was like, what the f is wrong in our simulations? So then we went in and looked at what's actually going on. And so we looked at the barycenter motion of this jet that is trying to form along the rotation axis. And what is actually happening is that you have like a kind of spiral motion going on that gains in amplitude. And this is what you see here on the left, is that you have an exponential growth of this barycenter displacement away from the rotation axis, which is prohibited, of course, in the 2D simulation, since everything is imposed to be symmetric. And then this saturates. So this looks like an instability in some sense. And we went in and looked at it, and so basically one of the instabilities that can happen is an MHD Kink instability, which is actually something that's well known from fusion reactors, where you basically have a plasma flow being confined by a toroidal magnetic field configuration. And this magnetic field configuration, if the toroidal field is too strong, is actually prone to this MHD Kink instability, which is just, kink here just stands for m equals 1, so basically just like a global m equals 1 displacement, which if you put it together with rotation leads to this nice little spiral motion. One of the key things for this kink instability to actually go unstable is that it needs to be opposite to the magnetic field helicity, which is here indicated by this arrow in magenta. So kink instability, I've already mentioned this. So you basically have this plasma column here confined by a toroidal field, and then basically this has been studied in a lot of detail in the fusion reactor literature. So there's a key kind of instability criterion where basically the toroidal field over the poloidal field ratio, if that is combined with the geometry of this plasma flow cylinder, basically leads to an instability if this toroidal field is too strong. And we looked into it, and actually that works out well. So basically the estimates for the growth rate and the instability and the wavelengths of this instability actually works out well in our simulation. So it matches roughly with what we measure from our simulation. So this is nice. And so basically now, let's have a look at how this looks like in 3D. And you're going to see the same entropy rendering that we've seen before as a slice in 2D, now just a 3D simulation. So initially you have this jet that wants to push out, but actually fails. It falls back. For a while it looks like there's actually not much going on. So this is rotating in and out of the plane of view here. So that's why it looks like it's wobbling around. And so you see the time here in the top part, which is like in milliseconds post bounce, so we can only do like the first 200 milliseconds post bounce actually. But at around 100 milliseconds post bounce now, something is going to happen, and you see bipolar, some kind of outflows that are pushing out along the rotation axis, which is the up axis here. But those actually don't stay nicely confined, so they actually like wiggle around, they twist, they deform, and basically they lead to this whole thing becoming like these two giant bipolar lobes that are driven by magnetic outflows, but actually don't look at all like a jet explosion. So you can basically see how non-axisymmetric this whole scenario is. And to show you one more simulation, this is now the magnetic pressure, the beta parameter, which is basically the fluid pressure over magnetic pressure. And basically if something is yellow, that means it's magnetically dominated. So we wanted to figure out how do these outflows actually come about. And initially you don't see much, since the color map is chosen in a way that it highlights what is happening at later times. So there's not much going on for now, but you see already some yellow kind of regions forming. This is basically here where the shock at this time sits roughly. And then at these times where we saw the entropy volume rendering expanding, now you see that basically there's all this yellow material being expelled from the protoneutron star, which sits in the center here, and basically rotates around rapidly, and these yellow streams basically get twisted and tangled and lose their kind of confinement around the rotation axis, so that they basically dominate the behavior at late times, but they're not able to drive a jet explosion. So what does it tell us? So we basically see these highly magnetized outflows, and they are conditions. They show conditions that are plausible for nucleosynthesis, for possibly even making the R process, which is basically a proposed way of making heavy elements from these very extreme core collapse supernova. So this has been studied before on the basis of these jet simulations in 2D. And we show in 3D the conditions are at least the same, but we actually don't launch an explosion. So depending on what is happening later on, since our simulations only cover the first 200 milliseconds post bounds, we might still have a side of where this process could happen, but we need to figure out if it actually gets expelled or not. Since if the material stays in the star, then this doesn't help us. But more important is that we may explain with 3D simulations actually the asymmetries that are observed in true supernova remnants. There was this recent new star observation paper of 44 Titan mapping in CAS A, and they actually showed like not at all. They basically ruled out a jet explosion based on a rapidly spinning progenitor, since they basically did a model in 1D or 2D and then basically showed that they observed asymmetries are not at all reproducing what would be believed to happen from a 2D simulation. So basically our simulations tell everyone that we need to basically do this in 3D if we want to figure out how the distribution of the asymmetry actually looks like in detail. The key thing, I guess, for long gamma ray bursts is that there's basically two proposed engine models. One is this rapidly rotating protoneutron star in the center, which is a magnetar driving this jet, which was supposed to believed to be the key engine model from 2D simulations. In 3D, we show that this actually doesn't work, and it doesn't look like this will work even if we continue the simulation longer, since these instabilities will always affect the propagation of these jets. What we, however, can possibly do is that there's this other engine model, which is a collapsar. So in that case, you don't have a successful supernova. You actually form a black hole, since the supernova is not blowing away the outer star material. It accretes and keeps on accreting until you hit a threshold and actually form a black hole. In that case, you form an accretion disk around that black hole, and you might be able to drive a jet from this black hole. So this is the other engine, and this is called what is called a collapsar. And based on our simulations, we would rather favor this scenario, since we don't really see how we will launch an explosion, even if we continue this run longer. So let me summarize. We've basically employed these large 3D simulations on blue waters, and blue waters was crucial in actually making these simulations possible. Core collapse simulations are an interesting scenario to study. It's very rich. It has a lot of physics in it, a lot of different scales. We've shown that in 3D, these MHD-driven explosions actually don't work in the way they were believed to work, since we have this kink instability disrupting the jet outflows. And based on the outcome of our simulations, and depending on how this goes on, if we run longer simulations, we actually might favor this long gamma ray burst collapsar engine. And with that, let me thank you for your attention.